Stoichiometry. Okay. So there is the usual handout here about all the stuff that we're going to cover in this unit.
Yes.
Sounds bad. Sounds bad. All right. So what we're going to learn how to do here is predict the future. Future prediction. Okay. So we're going to learn something here that's called a BCA chart. BCA. Just hang with me before we get there. The reading up at the top. Stoichiometry is the process of determining how much product is made or how much reactant is needed during chemical reactions. As we know, in chemical reactions, atoms are conserved. This means they don't disappear. We know this in a balanced chemical equation. And we did balanced chemical equations in our last unit. In a balanced chemical equation, we can learn two things. What substances begin the reaction, the reactants, and what substances we end with, what are the products during the rearrangement process. We also learn from our balanced chemical equation the ratio of the particles involved. We can see this ratio either as a ratio of individual particles or as a ratio of moles. Have you guys encountered moles before? Maybe. Not like the animals.
Science fair, yeah.
Science fair. Woo! Okay. In the lab, it's only practical to work with moles of substances rather than individual atoms or molecules. Why is that true? Yeah. Can you imagine having to count individual atoms? Firstly, there would be a lot and you'd be counting forever. The other problem is, how would you even do that?
One.
Exactly. You would count. But like it'd be difficult to see them, so you'd have a problem. And so what we're going to do is use our balance equations that we've already practiced doing to be able to describe things as mole ratios. So for example, here's an example equation. If we have 2 of magnesium plus 1 of O2, we get 2 magnesium oxide. And what this is telling us is that for every 2 moles of magnesium we burn, we have to use 1 mole of oxygen gas, that's diatomic, to produce 2 moles of magnesium oxide. So 2 moles, here's our ratio. 2 moles magnesium, 1 mole oxygen, 2 moles magnesium oxide. That's the ratios of our reactants and our products, is all compared to each other. So we can use this to make predictions, predict the future, guys, about how much we need of something or how much we can make from the stuff that we have. You guys ever do things like this? You like decide to make a recipe and you have to look in the kitchen to see what you actually have on hand. So if you want to make chocolate chip cookies and you know you need 3 cups of chocolate chips, if you look in the cabinet and you only have 1 cup of chocolate chips, you need to reduce everything else by 2/3 so that you don't end up with those sad cookies that I get at the end of my batch where I have no chocolate chips in them. Does that happen to you guys? I'll scrape the bowl and get another cookie, but it has no chips in it. No? Peanut butter cookies? I love peanut butter cookies. They're very good.
I made cookies yesterday and I had the opposite problem. I added too many chocolate chips. Like it didn't stick together.
That's not a problem. I like to do a 12-ounce bag of chocolate chips and then like a 12-ounce bag of M&Ms. The chunks? Those feel like artisanal to me. Like, oh, I made fancy chocolate chip cookies now. These aren't Toll House.
White chocolate in them, and then it's
White chocolate macadamia nut cookies.
White chocolate?
White chocolate macadamia nut cookies.
But they're like not. It's not even chocolate.
Yeah,
it tastes good.
It's just butter.
Cocoa butter.
Okay, so in order to be able to help us make predictions, we're going to start using something called a BCA chart. All that a BCA chart is a way that we can organize the information that we have so that we can predict the future. Tess looks skeptical.
Yeah.
Sorry, skeptical Tess. Okay, so sample problem. This kind of walks us through it. Okay, so there's a bunch of stuff on the next 2 pages, and it's already typed out for you. It's just stepwise going through what this is. So our sample problem says hydrogen sulfide gas, which smells like rotten eggs, which is true, Burns in air to produce sulfur dioxide and water. How many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide? What?
This is all weird problems.
Yeah, you'll love it. There's also math. Okay, so the first thing that we have to do is write a chemical equation for this. So here's our chemical equation. Hydrogen sulfide plus oxygen yields sulfur dioxide plus water. And then we have the coefficients in front that balance everything out. 2, 3, 2, 2. So that's step 1. Step 2. Underneath our chemical equation, we write out how many moles of everything we have before the reaction takes place. We're told that we have 2.4 moles of hydrogen sulfide. We're told that it has to burn in air. This, you see X, that's not extra small. That means excess, like it's an abbreviation for this, so that you don't have to write excess every time. Get it? X, S, X. Yeah. So what that means, it's kind of like the same as saying infinity moles. Like you have as much as you need. Don't worry about running out. You're not going to run out. And of course, before the reaction happens, we don't have any product yet. Is it possible we could have some product? Maybe, but not in this problem, right? We're not told in advance, you already have a mole of water. We're not, it doesn't say that. Okay, you guys ready for the next step? Questions? You guys doing okay so far? Okay, so next step. We're told we're going to consume all of our hydrogen sulfide, right? So we're going to lose 2.4 moles. What we have to do now is figure out what the change is going to be for the other things in our equation. Here's one trick, guys. If you look up at your coefficient and you have other things that have the same coefficient, the number of moles change is going to be the same. That's handy, right? So then where did this 3.6 come from? Here's how you get the 3.6. We know that we're going to use 2.4 moles of our hydrogen sulfide gas. If we want to know how much oxygen we're going to use, we need to use that mole ratio that we talked about before. So remember, that would be like saying 2 of these to 3 of these to 2 of these to 2 of these. So you guys remember dimensional analysis and how Dr. O'Malley told you it would come back in the future? Oh no. See here where it says moles of hydrogen sulfide? These coefficients also tell us moles of hydrogen sulfide. And so we're going to use these coefficients to make a conversion factor that we're going to use to predict the future. So for every 2 moles of hydrogen sulfide, sorry, I should write 2 mole there, shouldn't I? We'll abbreviate in the future. There it is. For every 2 moles of hydrogen sulfide, we're going to produce 3 moles of oxygen. So this conversion factor is coming directly from our coefficients in our balanced equation. And if we multiply 2.4 times 3 divided by 2, what are we going to get? It's like 1.5 times the 2.4, right? So I've got 2.4 times 3 divided by 2 gives me 3.6. And because we're using it, we're going to give that a negative sign. Also, you guys see in this conversion factor, we can cancel some units. Isn't that nice? It's tidy, right? What do you mean? So if I do 2.4, times 3. I get 7.2
Oh.
divided by 2, 3.6.
I got it. Wait, can you say why it's negative?
Oh, because we're using it up. And so this line is telling us the change. It, like, if we imagine that we took these two things and we put them in a jar, and then a reaction happens, and then what do we have left? So we're going to use 2.4 moles of hydrogen sulfide. We started with more oxygen than we need. So we're going to use up all of our hydrogen sulfide. We're going to need to use 3.5 moles of oxygen. And what we're going to produce is 2.4 moles of sulfur dioxide and 2.4 moles of water. And another way you can think about those is if we start with our 2.4 moles of hydrogen sulfide, and we can make other conversion factors with this equation. So we could say for every 2 moles of hydrogen sulfide, which is this part, I'm also going to make 2 moles of sulfur dioxide. So then it's my moles multiplied by 2 over 2, which is the same as multiplying it by 1. So we're going to end up with 2.4 moles of sulfur dioxide. And that's where this number comes from. And this number is this one. So far, okay? All right. So then we're going to do is do some more math, right? We're going to see how much we ended up with each one. If we start with 2.4 moles of hydrogen sulfide and we use up 2.4 moles, then when the reaction is over, so after, we have 0 moles left. If we start with excess moles of oxygen, think about it like infinity moles, and we subtract 3.6 moles, we still have infinity moles of oxygen. Next, if we start with 0 moles of sulfur dioxide and we increase what we have by 2.4 moles, then after the reaction happens, we're going to have 2.4 moles. Same thing with water. If we start with 0, we generate 2.4 moles in the reaction, we're going to end up with 2.4 moles. So to answer our question at the beginning, how many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide? That's going to be this number. This was the thing that was our answer. Did we do stuff we didn't have to do? Yeah. So to answer this question, we could have gotten by with just doing this part. This helps us organize everything, though, so we kind of know what's going on. We didn't really have to do these. Down here, it says if mass is required, convert moles to grams the usual way. Do you guys remember doing this? Now we've got 3.4 moles of oxygen. And to figure out how many grams we have, we're going to use a conversion factor that says every mole of O2 weighs 32 grams. And so you could multiply those moles times grams to get the total grams of oxygen you would need. Tess, you look so skeptical.
Why is it 32 grams?
It's from the periodic table.
Oh, okay.
You remember when we were doing those?
I can't say that I do remember.
Cannot say. You guys watch The Office. You can't say or you won't say. Or you don't know. No, just kidding. Okay, so on our periodic table, we'd figure that out by looking at oxygen. Oxygen has an atomic mass of, zoomed in for fun there, of 15.99. So if we have O2, we're going to need to double that.
Okay.
Oh.
You guys remember that, right? Yeah.
Cool.
Stoichiometry is where all of chemistry starts to come together to predict the future. Okay. So we're going to take a look at worksheet 1. You okay? Whew. For each problem below, write the balanced chemical equation, identify what is given and what you need to find, use coefficients from your balanced equation to determine the mole ratio, show your setup. All right, so first one. We're going to start with reading the question. Oh, we already did this one. That was our example. Number 2, propane, C3H8. You guys have seen propane, right? It comes in a tank. Hook it up to your gas grill. I'm not a gas grill person, sorry. Burns in air. So I'm going to set up my equation here. I'm going to set up a column for this. And I leave like lots of space when I'm doing these. Burns in air, O2, to form, which is yields, carbon dioxide, CO2, and water. What kind of reaction is this? This is a combustion reaction. So first thing we need to do is balance this thing. If I have one of those, I need at least 3 of those, right? If I have 3 of those, yeah, I can do this. Okay, so if I've got one of these, then that means I've got 3 here, and I've got 4 here. You all done?
Yep.
Thank you, sir. And then how many water or how many oxygen we would produce? We have 4 here plus 6, so that would be 5. Does that look right to you guys? I think it's right.
Yeah.
Okay, and then it says if 12 moles of carbon dioxide are formed. So if it says that they're formed, that's telling us that that's what happens in the change, right? So I'm going to write 12 moles down here. How many did I start with? It says, so think about your equation as being separate from your BCA chart. We start with 0 moles of carbon dioxide and 0 moles of water because those things are products. And before the reaction takes place, we don't have any of them. Because it doesn't say we have any. What we need to find is how many moles of propane were burned. What we're looking for is this number. If I'm only concerned about how the carbon dioxide that I started with and the propane that I used, do I need to know anything about oxygen or water? Yeah, so am I going to do that? I don't have to. So the way I'm going to write this up is I know that I start with 12. This is the only number that I really know here, right? I could start with this, but that will get me nowhere. So I'm going to start with my 12 moles of carbon dioxide. And I want to know how much propane I used. And so to do that, I'm going to make a conversion factor using my balanced equation. And I know that for every 1 mole of carbon dioxide that I produce, for every 3 moles of carbon dioxide that I produce, I have to burn 1 mole of propane. So here's where those numbers are coming from. This number comes from here. This number comes from here. And this number came from here. All right, so 12 times 1 is 12 divided by 3 is 4. So that's the number that I'm going to put there. Then when I look at my units, moles of carbon dioxide cancel, and I'm left with moles of propane. Those of you who like doing math and numbers problems, you guys see how this is a 1? And then I've got a 5 and a 4? If the ratio is 1 propane to 5 oxygen, what number goes in the change for oxygen? If I apply that 1 to 5 ratio to 4, and I get, what did you say, Tess? 20, yeah. I'm going to have to use 20 moles. Right? Because it's 5 times the number I used here. And then for water, I'm going to have 16 moles. So when these are whole numbers, sometimes these are real. You can do these in your head. All right, how you guys feel about these?
Wait, can you explain how you got
20. I applied this ratio. So if I have 1 propane to every 5 oxygen, if I have 4 propane, then I'm going to have 20 oxygen. You guys ready to try some of these?
Yeah.
Okay. So what I'd like you guys to do, whoops, that's wrong side. What I'd like you guys to do is try to, how far can we go? There's 4 more problems. There's 3 on the next page, and then there's 1 on the back. The one on the back looks scarier, but it's not that scary. So I want you guys to see if you can finish those before the end of the period. You can talk to each other if you'd like.